Okay, guys, in this video lesson, we're going to go down the road of torque as part of our next part of our unit, which matches up torque to simple machines and how we can use little devices to actually help us in our everyday lives. Okay, so today's focus is on torque, though. All right, so here we go. So what is torque? All right, now if we go back to previous parts of this year where we talked about work being inputted to cause some sort of movement because of a force over a distance, right? Torque is the same concept, but instead of trying to go linear with applying a force through a distance, we're doing a twisting motion instead. All right. So some things that we take a look at, like how do we open up a bottle of water or a bottle of pop, that kind of stuff. Okay. So simple things like that. So for example, I just got I'm gonna chill here, my little water here. If I want to open this lid or this cap, how do I open this up? Well, I had to provide a force to twist. That force that we were providing to twist is called torque. Okay, so I put my fingers on it and I'm going to twist and create a pivot here, and that is going to allow me to open it up, and that's applying torque across my bottle cap. Okay, so torque is done anytime you create this rotational motion about a pivot point. All right. Now, one thing we got to be aware of is that this bullet point kind of 3 here, that force is applied at a location away from its pivot point, all right? So if we actually take a diagram of that bottle cap here and we take a look, the pivot point actually, if we take a look at that, that pivot point is inside of here. That's where the pivot is happening, right? So it's pivoting around this axis right here. Now, the force that we are applying to cause it to pivot is out here. So we're applying a force to create that twisting motion out here. So the force is away from the pivot. So there's a separation there. Or we could say that there is some sort of radius between the pivot point and the force. Okay, so that's helpful for us because as we move forward, radius is going to be part of our math. Okay, because it is a force causing a movement or a rotation through a distance, it's work. Okay, so it's an application of work in a twisting motion. All right, so you can kind of think about it as twisting work is probably the best way to visualize this as we move forward. All right, so here's our equation. Okay, first thing we want to deal with is what's this kind of squiggly looking T thing. All right, the squiggly looking T thing is actually the Greek letter tau. Okay, it's the way that we symbolize torque. We start getting to some more Greek letters as we go through different physics topics because our alphabet gets used up. We already use T for time. We already use capital T for period. So T is getting used a lot. So now for torque, we use that Greek letter tau instead. So what we kind of do is kind of a lowercase, capital, italicized kind of T looking thing is what I kind of draw it out like. All right. We of course have to apply a force. That force is multiplied by that radius or that separation between the pivot point and the applied force. So we have those two things. And the last piece of the puzzle has to do with at what angle are you applying the force, okay? So you need to have the proper angle so all the force you apply creates all the twist, all right? If you apply a force in the wrong angle, you won't actually create the twisting motion that we want, okay? So we want to take a look at that angle here in terms of, and now in this case it's sine. So up until this point, most of our equations that dealt with applying a force and an angle, we were using cosine. Okay, there's a reason why we use sine, and we'll get to that here in a minute. But make a note of it. This is sine of theta now, not cosine. Okay, so our equation deals with sine instead. All right, let's take a look at how this kind of works. The reason why it's sine is when you're looking at torque and the forces it provides, only force perpendicular to the lever arm provides the torque. Okay, this is very different than linear motion where the forces had to be parallel with the motion. For torque, because we are twisting and causing a rotation, the force perpendicular is what provides the torque. Okay? If you think about it, why is this the case? Well, if you want it to twist, you want to have a force that's running tangent to that circular motion at all times. Okay? And then if we take a look at this idea back to our equation, okay, what happens when the sine of 90 or sine of theta is 90 degrees, okay? So if you punch that into your calculator and you say, okay, let's take a look here. If I take the sine of 90 degrees, hit enter, I get 1, okay? So what we're saying here is if you have a 90-degree angle, so your torque is perfectly perpendicular to the twist or to the circular motion, that means your sine of 90 is 1, or 100% of your force is being applied to cause that twist. Okay. Now, also that lever arm. So we also talk about that radius. So that lever arm we're talking about, or the radius, okay, is that length from the force on that handle, okay? So if you are not applying a force perpendicular, it's only the perpendicular force to the handle that causes that torquing on that object, okay? Not twerking, torquing, okay? A little different. Now, let's take a look at that in terms of how we can visualize it. So here's a nice wrench, okay? Torque is used in a lot of mechanics because we use tools, and humans, as tough as we are, we're not that strong really in comparison to the things that we build and the structures that we work with. So we use tools and wrenches and screwdrivers and saws and all these simple tools to help us do a lot of more work, not more work, to change the amount of force we need in terms of the work that we're doing. Okay, we're going to find out later on it's not more work we're getting out of it. All right, so here's how torque works. Okay, we need a pivot point. We need a radius. Okay, so imagine if you grabbed the very end of this wrench right here and you pulled on this wrench. Okay, now you can pull at lots of different angles. All right, if you pull straight out, okay, so you have the wrench on the bolt and you grab the wrench and you pull this direction, right? That would create no torque because you are 100% going parallel with the lever arm. As a result, that component wouldn't cause any torque. In fact, all it would do is have the wrench kind of pull off of the bolt, and you don't want that. Okay? If you pulled at any angle between here and here, this darker blue line kind of represents one example of that, some of your force would go into twisting this, but some would also go into pulling it away. Okay, so again, not something you really want. So when you're turning a wrench, you don't want to pull away and across. You want to pull it straight perpendicular to the actual lever arm. All right. So because of this, now if it's perpendicular, 100% of this force being pulled, okay, making this be the sign of this is a 90-degree angle here, 100% of that force now can be applied to create torque. All right. So what you're looking for is a 90-degree angle to create the most torque. Okay. Now, is it true that sometimes people pull inwards a little bit on a wrench? Yeah, that's absolutely true. And they do that often because they want to make sure that the wrench doesn't slip off the bolt. So they want some of the force to be pushing inwards to kind of press the wrench against the bolt and then allow the force pulling it perpendicular to allow that twisting motion. Okay, so it's very common when someone does it that they do pull inwards, but they're not getting 100% of their force into the torquing motion in this case then. Okay, so let's take a look. Yeah, obviously we want to cross this guy out because that's not providing torque here. All right, let's take a look at this kind of conceptual problem here. Which of these force vectors will generate the most torque to tighten the bolt? Okay, I asked, yes, I'm requiring you to have a little bit of knowledge on how do you tighten bolts versus loosen bolts. All right, if you don't know that, look it up. Talk to somebody around you. What's that? What force vector will generate zero torque on the bolt? And if you try to loosen the bolt and the wrench keeps slipping off, what's the most likely torque vector you are generating? Okay, so answer these three questions. We'll pause the video and then we'll come back and talk about the right answers. All right, so if you want to tighten the bolt, okay, we have a thing that we always say, righty-tighty, lefty-loosey. Or if you go clockwise rotation, that tightens up 99% of the bolts that you'll ever work with. Okay, there are exceptions to that, and if you want to know about those, I'd love to talk about them because a lot of them involve bikes, and I love bikes, or other type of automotive kind of things that rotate and spin on axles with pedals. But most of the time, when you turn a bolt, almost always it's righty-tighty, lefty-loosey. So you are going to the right. So what's going to generate the most torque? B will generate the most torque. Okay. C will generate no torque. D will loosen it, and the wrench will be pulled off. Okay, so that would be the bottom one here. So you would actually pull backwards. You'd be loosening the bolt, and it would probably slide off. E would be the direction you would pull if you wanted to break the bolt free and loosen it the best way, provide the most torque to loosen that bolt. Okay, and then A, while A would work, it is not necessarily the one that we want in terms of providing the most amount of torque. Okay, so that's a little difference between those. All right. All right, guys, we'll end the video lesson here. As you probably can hear, there are lots of kids coming in to take their final. Thanks.